Hello everyone, welcome back to Calculus. This time we are studying section 3.7, derivatives of inverse trigonometric functions. And if you are following the textbook, just make sure you know there are other materials and topics on the textbook. But anyway, for my class, the requirement it is for this section 3.7 the derivatives of inverse trigonometric functions. Besides, you really also want to know the requirement for this class. You only need to know the formulas. You don't need to know how those formulas are derived. Okay, so simply put, the objective for this part of discussion, it's all about three formulas. Derivative of arc sine. Sine inverse of x, it is 1 over square root of 1 minus x squared. Derivative of cosine inverse of x, or derivative of arc cosine of x, well, it is negative. Negative, the same expression from arc sine. And then the third formula, it is a little different. Derivative of tangent inverse or arc tangent. Okay, it is 1 over 1 plus x squared. Truthfully, in calculus 1, we may not use a derivative of arctangent or tangent inverse a lot. But anyway, I still want to know this formula because if you need to move to calculus 2, and indeed we need use this tangent inverse a few times. There are several topics involving with derivative of tangent inverse. So again, simply put, the requirement for section 3.7, it is about those three formulas. Okay. How about let's take a look at how we handle those formulas. Remember in the previous section, really it is about chain rule. So certainly, mostly for the problem on the homework and on the test, you may not expect a simple derivative of those simple inverse trigonometric functions. Mostly they will have to be combined with the chain rule. So the first example I took from the textbook, it is to find out the derivative of sine inverse of 2x cubed. Now this part really requires a chain rule. So what I did, if you remember the chain rule, usually we are going to create a notation that will make the function in a basic form of a common type of function by taking u as 2x cubed, so y can be considered as sine inverse of u, right? The reason we want to consider sine inverse of u, remember the DD notation actually, I am using DD notation actually. Pretty much recently I don't use prime notation at all for the past 2 weeks or for the next few weeks. For the derivative, I prefer use the DD notation. So the derivative in terms of the derivative for y in terms of u, it is just from the same formula because y is sine inverse of u. Okay. At the same time, u it is created with this formula, and it is a function of x, right? So we could have du dx. And then according to the arrangement of chain rule dy dx, it always can be found as dy du times du dx. And again, one more time, okay, this part of the comment I'm giving here, it is only for to remember how to remember the formula, okay, nothing about the cancellation. When you write down the arrangement for the chain rule to confirm, looks like du is cancelled. So that is the arrangement of the chain rule, okay, for dy dx. And then I write down, then I replace each notation with the formula we just calculated, dy du, then du dx. I multiply them together. Clearly, we don't expect the final answer as u and x mixed. It should be x only. So we put this u back to x. That is my answer. Derivative of sine inverse arc sine And clearly there's a chain rule involved. And the next one, also the chain rule involved. Okay, we want to find out the derivative of tangent inverse of x squared. Remember, I think I specifically mentioned the derivative tangent inverse a moment ago. Okay, we may not do a lot of work for tangent inverse for now, but anyway, we will do a lot of work for tangent inverse in calculus 2. So let's take a quick look how we understand the formula correctly. Again, there's a chain rule involved. First, I take u as x squared, and then, well, that fits the formula precisely. But to write it correctly, the derivative I got should be dy du, which is 1 over 1 plus u squared. At the same time, I can have du dx. And again, according to the chain rule arrangement, dy dx, it is a product of those two derivatives. Still, we really don't want to have u and x mixed. We get an answer back to x only. And that should be it. That should be it. Maybe we still have some time. Take a quick look. Another example. Example 3.66. And this time, well, actually, if you look closely, we do have arc sine inverse precisely, right? But anyway, there's x squared in the front. So this time, as I'm saying, math, it is always it is a challenge, and it is always a challenge. Certainly, each individual topic of math, it is very hard. Like the chain rule, like the derivative of the inverse trigonometric functions. Besides, many times we will have to combine the new knowledge with the old things we have learned. So example 3.66, it is exactly the case. Similarly, we do have sine inverse of x exactly, but anyway, there's x squared in the front. So my response here is actually, I'm seeing this function as a product. So certainly when we work with derivatives, there's a product. I'm saying that is the product rule. Okay, so I repeated, copy and paste the formula for the product rule. And then I'm taking u as x squared. I'm still using notation u. I hope you do see this is different from the approach of the chain rule. Okay, this time I'm using not only u as v. I'm doing the product rule. So u is x squared, v is sine inverse of x. Then according to the arrangement of the product rule, we need to have u prime, which is easy. V prime, actually it is just from the formula we just covered, right? 1 over 1 plus x squared. And then the thing is, you want to combine them together, put them everything together. So u prime v plus u v prime. I would say if, well, actually, lucky in this case, there's really not a lot of simplification. You may want to keep the answer as it is. The only thing I did, well, for the next line, I just feel for this fractional part, maybe make it clear x squared it is part of the numerator, or it is just a numerator. I'm just move x squared to the top, and then I keep everything the same. I guess I really want to say in calculus, well, you don't have to work too hard about the simplification part. Make sure you do show perfectly the calculus work, derivative of product, of quotient, and chain rule, those things. So I believe this is the topic of section 3.7. Derivatives of inverse trigonometric functions. Specifically, there are 3 formulas involved. I would expect you know those formulas very well. Indeed, I would say maybe you want to spend a little more time for the third formula, because usually we don't talk about tangent or not even tangent inverse at all. But anyway, the third formula, derivative tangent inverse, simply it is required for calculus 2. It is required for calculus 2. Okay. Hey, thank you for watching. See you next time.